Yeah, so now we're good. Yeah, so last time during the last lecture, we used a very concrete example to minimize a x quadratic minus 3 function by looking for the x. That's just only one variable involved. It's very easy and very simple. And using just that easy function, objective function, we actually understand the learning rate matters. The starting point also matters, and also the objective function, the shape of the objective function also matters. Are you in the steep part of the objective function, or you're in more like a plateau part of the objective function? So the reason why we don't like, so I think we covered that. So we talked about some kind of learning rate, we really do not like those. I think it's right maybe here. So we were saying, so we like to stay at one side. If your minimal, the best point is at maybe in the middle. I don't want to have a learning rate just kind of oscillating from the two sides. There's a reason there is, so if assuming you're in the good side, that big learning rate might just jump you into the plateau. And then the plateau region is actually pretty hard to jump out. So there's a reason why like this learning rate matters. Also the shape of this objective function also matters. So that explains, and so there's one figure I did, I cannot remember how I did it, so I just rewrote in my slides is, so if you use a crazy learning rate, if you're starting from this position like x0 equals 1, if you use this crazy learning rate, and this will push you to some positions like equals -2. So this actually shows the gradient descent not necessarily decrease the function. In this case, actually, it increases the function. I hope this point got delivered. So learning rate is very critical. So be careful what you pick. And this is like a dramatic, extreme case about a really crazily bad learning rate. Actually pushes you to be move to the loss regions even higher. Okay, so yeah, we talk about all those things you need to care. Starting positions, a learning rate. Think about the function of your objective function. And the last thing I want to mention is, how do you decide to stop? So in the homework, we ask you to actually look for, to plot a epoch versus the training loss, the graph, a figure. This is actually a very good figure to tell you how good or how close you are. So, and that error you're going to plot is the train MSE. We already talked about it. So this is not square sum of squared error. This is mean squared error. The only difference is really just you have a 1/n normalization factors. You still sum over all the error by taking a quadratic function, and you just do 1/n to normalize based on number of samples you considered. So there's a reason why you do this, but we're going to do this in the next lecture. Is so we normally use test MSE. We do the test MSE, right? So in the later, we want to actually evaluate something called bias and variance trade-off. And the figure, the epoch versus the training error and the test error can tell you a lot of things about your model choices. So we want them to be comparable. So that's why here we plot a training MSE, because it's a per sample error. It's comparable to a test MSE because that's also a per sample error. And this will become much more clear in the later slides and also in homework 2. So, but just keep this in mind. Again, so when do you stop? There are many different tricks or different rules. Homeworks, we just ask you to stop at a predefined number. A predefined number of epochs. That's not necessarily the best. So there are a lot of other tricks like you want to stop, you kind of measure the improvements, the decrease of that loss function when it's not decrease and more for a few maybe epochs or a few kind of the size of that value of the improvement is not increasing anymore. You stop. So there are many tricks. And homeworks, we just use a simple trick. So this is just to show you what type of discussion I'm looking for in your homework. So this is actually what I did. I just converted our template into a Jupyter notebook because I want to just make it visually. It's actually, so the reason why, maybe some other explanation, why we don't do a Jupyter-based template. So in general, a Jupyter notebook is really great for doing checking and visualization at the same time, coding, right? But I found that like encourage that coding practice. It's kind of linearize everything. But you know, in coding, it's really modular, right? There's a lot of function you actually should do modular, and then modulate it into a function. That's how our template trying to help you modularize it, and then you can reuse rather than just keep doing like a plot function, all those similar plot function, all those. So it's in the end, just I hope you like the direct coding, template-based coding, like our requirements, even though I know a lot of homeworks in this department, now it's the fully Jupyter-based. I still hope this can encourage you like a little bit about good coding practice. Yeah, modular design, right? That's all about it. Yeah, but of course, when Jupyter is so easily visualized, you can immediately just do the test, do the debugging on the fly. There's always the trade-off, good and bad. So in the homework, I pick the more pushes just purely coding type. Yeah, but you can use Jupyter, you know, just to prototyping and then visualization, like I'm trying to do here. So this figure trying to show what? Learning rate and the number of iteration also coupled. If you have a small learning rate, you better try a larger iteration number. If you try a smaller iteration number, it might be really off what you learned. And that training loss epoch figure might be still pretty high. You can actually tell from here. So this is actually the purpose why we plot training error, right? In the later, when we have the testing error plot, you're going to gradually see there are also the differences of training error plot and test error plot. That margin tells you a lot of things. So this is the later, like a bias and variance trade-off, and how do you figure out there's a bias or there's a bias. And mostly it helps you to figure out there's a high bias in your model. Yeah, so keep that in mind. It will be very clear in homework 2. Yeah. So now let's come to more the last part of the optimization. So like I told you, I mean, again, our nutshell, we covered so much in the search and optimization in this lecture. And in the end, I put the last part of discussion inside the model of parameters. It's because the choices of SGD or GD or norm equation is related to something, it's about the goal. So what type of properties you aim to make your program, because like I emphasized many times, right, we're using data to learn a program. And what type of property you look for, you aim for in that program. So this is roughly what I think. There's no consensus in the field yet. So in general, we want to have a model generalize well. predicts well on the future data, right? That's just the fundamental goal, and we emphasize many, many times. But there's some other goals, like we want it to be computationally feasible, computationally scalable, and computationally efficient, right? This is the computational angle. And it's not just a good model, but if it's not scalable to large amount of data, and it doesn't fit to a certain type of application, right? If this is a good model, but it doesn't really work well on the smaller type of data, and then that's a wrong fit, right? But you have to really think very carefully when you make choices, both this generalization perspective or prediction perspective, and also the computational perspective. And recently there's actually a lot more. It's about this trustworthy perspective. So we want our model to be interpretable, trustworthy, and robust, right? There's a lot of work about invading the machine learning classifiers, something called adversary examples. Maybe some of you already heard about it. So yeah, so this is the three things, and this is the focus on the last part. You have the model. Who is your parameter? And then what's the property of your model? What's the property to learn the model, to use the model? There are also two different phases, right? Is the learning scalable? Is the operational phase scalable? These are two different cases, actually two different situations. There's some model easy to learn, but very hard on the operational phase. And that's actually something we're going to learn in the future, like a k-nearest neighbor approach. It's super easy to learn, but very hard to scale up in the operational phase. And this is the consideration. Again, so why do I care to talk about here? So in the end, stochastic gradient descent versus the normal equation versus the gradient descent is, it's very useful to use stochastic gradient descent to fit the data with massive data sets. Because you really do not need to have all the data to fit into your memory, right? You can just do one at a time, or a batch at a time. And that's the comments I had. You have to consider your computer, the property of your current GPU or CPU or the memory size, then consider that the batch size. The size of the batch is related to the computer resources you have. And of course, because this stochastic nature of this observation method, it also fits very naturally to the online setting, which is a streaming case. Your data is not available all at once. It's coming in one at a time, or maybe like at some temporal resolutions. And those are also fit and make stochastic gradient descent a very good candidate in those online settings. So it's about efficiency, also about feasibility, right? It makes the streaming case training or data fitting feasible. And the classic norm equation of gradient descent is just not feasible in the streaming case. So that's about it. And then how do you pick B? Again, this needs your knowledge about computer architecture. Of course, in your current problem, you have such a smaller data, it actually doesn't matter. Yeah, but yeah, so the homework, just again, a little bit about homework. So a lot of other machine learning, first homework, they start to let you work on a real world regression data. But in our case, we just pick such a simple data, so there's some kind of reason behind. This is actually the reason, because it's super easy to plot it, and it's super easy to see how the learned model and how it fit with the scatter plot of the data. Whenever you have 2D, actually 2D is okay when you have more than 2D, it's just no way to visualize the data. It's very hard to observe the relationship of the fitted hyperplane versus the distribution of the data. So we try to start from simple and easy to visualize, and the most important in the discussion is about how those factors in gradient descent, stochastic gradient descent, did you try those? How do them influence the optimization, influence the training loss versus the epoch curve? So that's what we look for. And I hope this type of discussion help you understand all those 4 variations a little bit more deeply. So that's the goal. Questions about homework? And also don't remember this number because I did a trick in my gradient calculation. And if you do not use that trick, your learning rate highly likely is not this one. I did the trick, it's called a normalized gradient. You can try the trick if you like. You can check it out, but this is not required.
Is that just putting a constant in front of your learning rate?
Yeah, you actually normalize the gradient with the number of samples.
Okay.
Check it out. There are actually a lot of variations.
There's one that was like 2 over m and some derivations.
Do you mean the derivation? I don't want to put it here because there's so many variations with how you calculate that gradient, normalized, unnormalized. So there's a full paper I put in to read in the schedule. Actually, please read that if you're interested in more advanced implementation there. Okay. Yeah. So there's a very good review paper has covered almost all the possible tricks in that paper link. All right. So and there's the other reason, right? So there's the efficiency reason. There's also the other reason is because the optimization. So like gradient descent use all the training data to just calculate one update gradient. So again, I hope you still remember what is gradient. It's really just a change vector on your the previous theta in our case, right? It's a change vector. And that change vector is keep updating with the different iterations. And really a precise calculation of that gradient is not very necessary because you're going to recalculate it anyway, right? Because every step, the gradient you're using is the gradient at that specific theta t. You calculate theta t's gradient and use it to update theta t, move it to theta t plus 1, right? So very precise calculation is actually not that very necessary. So approximated solution at a lot of cases is already good enough. It also adds noise. The noise is implicit regularization. Actually helps in general help you converges actually rapidly and faster. So what do I mean regularization? That's the lecture 6. I'm going to talk later. So what do I mean regularization? So, but anyway, so you better to get a noisy estimate and move rapidly because for every sample you're going to update your theta. Now, like gradient descent, you calculate the summation by applying the model on every samples and then calculate that gradient vector. It's a really costly calculation. So this is a table. I don't want to redo it again. So, but it's like more comparison of stochastic gradient descent, and all those in the middle. So stochastic gradient descent gives you very noisy gradient updates. And mini batch is a little bit noisy, and gradient descent is precise. Because that's exactly a precise gradient vector we calculated. And the stochastic gradient descent is only one sample, right? And mini batch needs B samples, and gradient descent needs all the samples. In the case there's a large massive data, a lot of cases there's just no way you fit all the data in your memory. And so in terms of big O, the stochastic gradient descent is O1 gradient at calculation, one sample gradient at calculation. And this is really tricky. In the mini batch version, if let's just naively a little bit abusing of the concept, if you have B parallel threads, you actually feed all the B that a mini batch is B samples, right? you feed each sample to a thread. You really do this one single stochastic gradient descent calculation and do B of them all at the same time. So that's why the cost is only still O1. It's all A sample calculation. Of course, this B matters, right? Yeah, so this is the tricky part. How to calculate B, yeah, so we're not going to talk about it. Feel free to think and then maybe read some more advanced papers. And here you just have to calculate all. Question about this? All right. So to summarize, we have normal equation, gradient descent, stochastic gradient descent, mini batch stochastic gradient descent. I already covered pros and cons for each, so feel free to read them more carefully. And I think this summarized, yeah, so, okay, so this page I already covered it before, and this is like the, yeah, so this is the normal equation cost. And this is, you can use this to calculate the gradient descent calculation. So this is P times N times 1. You actually can just do calculation. So there's also N times P times 1 here. So what is these, the cost should be very easily derived from the previous equations. Yeah. So I'm not going to do it. And then the last thing I want to talk about is the connection of iterative gradient descent or stochastic gradient descent method versus the normal equation. So again, normal equation is our solution, and we know that very clearly because the properties of this J theta function. And the iterative approach starts from random and keep moving to something. And how can you guarantee your endpoint is close enough to the normal equation solution? You actually can prove it. As long as this is satisfied. Alpha is the learning rate, and I hope you understand what is the lambda max here. I'm not going to cover it, so if you're interested about why, so there's actually a lot of paper talk about this. Feel free to check them out. Yeah. So this is whole everything I want to cover in the optimization of linear regression, and that's it. Just before I move to lecture 5, questions about lecture 4? Alright, so now let's move to lecture 5, which it's a very easy extension of linear regression, but it involves something very, very useful for the generic machine learning, which is about the model selection. So again, so this is where we are, and this lecture 5, focus on representation. So in the linear regression, linear regression, we have only this form, right? Theta transpose x, and that's all we have. But given the x features, we learn a weighted linear combination to predict y. So now we just do a very simple extension, something called linear regression with nonlinear basis expansion. And the whole thing it really does is to change the x to something called phi x. And then everything else is all the same. Scoring function is the same, search method is the same, the model is also the same, still those theta parameters. The only thing changed is here. So let's see then what is phi x. So again, look at this form. In the linear regression, we have x transpose theta, or theta transpose x, so don't get confused about this, right? They are the same thing. We sometimes write theta transpose x, sometimes write x transpose theta, because the inner product gives you a scalar. So this is exchangeable, the order is exchangeable, so they mean the same thing. Okay, so this I emphasized many times. We use this trick in deriving the loss function, deriving the gradient. It's really all in this trick. If you understand the trick, all those scary functional matrix looking, they're not scary at all. Yeah, just keep that in mind. And then in this formulation, we just change the x into phi x. So what is phi x? So again, just summarize, we change theta x, and the phi x is really just theta 0 plus theta 1, phi 1, theta 2, phi 2, theta 4, phi 4. So if we write it, it's just theta 0, theta 1, to make theta m in this case. So this is my theta vector. And my phi vector is 1, phi 1x onto phi mx. Yeah, they're all depends on the phi and the size varies. Okay, so phi sub jx are predefined basis functions. So for example, in the simplest case, we can have a quadratic x quadratic added into the old x. And then that gives our phi x is just 1xx quadratic. And the previous formulation, what we had in the linear case, we make our x vector is 1 and x, right? And now we just augment it with a x quadratic term. That's one choice. So what's the influence of this choice is it makes us to be able to fit this type of lines. So rather than fit only in the linear lines, we can now fit quadratic lines. Question about this? So this is theta 0 plus x. So this line is theta 0 plus x theta 1. And this is theta 0 plus x theta 1 plus x quadratic theta 2. Of course, it can represent, it's a quadratic line, right? Just by definition. Yeah, and the good part is by converting x into phi x, you can convert every training sample into phi x training sample, right? And you get a matrix of phi, and then solution, whatever you did in the linear regression case, all work by replacing the x matrix, the old x matrix n times p, into this phi matrix. That's it. Nothing else. See, this is still our normal equation solution. Phi transpose phi should inverse phi transpose y vector, and that's still your solution. Gradient is still the same form just by replacing the x matrix into phi, and you still do the same gradient descent. Same stochastic gradient descent, same mini-batch stochastic gradient descent. But this actually can learn much more complicated curves, much complicated fit and a model. So this is the 1D case. If you have original feature like 2, x1, x2, we actually emphasize the linear model in the 2D case. It's a plane, right? What you learn is plane. And you can also augment this x into phi x by adding x1 quadratic and x2 quadratic. Then what you learn is more like a half dome shape, like a bell shape or bowl shape, something like those. Of course, you can also add maybe x1 times x2 term. And this really increase the flexibility and complexity of your model to be able to fit much more complex curves or surface. So I hope you still remember, this is a surface map view. This is a surface map view, but this is not about loss function. This is actually about our y versus the x, right? In the previous lecture 4, we always just plot the loss function. In there, our parameter are theta, and in here, this is still a surface map, but we're plotting is the y and versus the x. And so all the current phase, we assume the basis shape is given, which means I know there's a term there, I know a term there, I just need to look for the theta. Theta before x1 quadratic, theta with x2 quadratic, and make theta 5, actually in this case is 6, to with x1 and x2 interaction term. Very easy, again, solution is phi transpose phi inverse phi transpose y. Okay, so that's the simplest case, right? You only add quadratic terms, but the popular basis functions are a little more complicated, and these are the popular basis functions. In general, their polynomial is, they all have this form is x power of j minus 1. So if you put j equal to 1, it gives you 0, right? That gives you first item is 1. It guarantees the first is the pseudo feature, and the second is the x, third is x quadratic, and then x cubic, and until x to the d. And the shape of polynomial basis is this, and actually is this. So for the even numbers, it's always this kind of bell shape, right? Of course, it's quadratic. Power 4, power 6, right? It's always positive. And this is the odd number basis. So this is the cubic, power 4, power 7. They all have some kind of shared shape, but they're different, actually, like the slopes. So this is the odd polynomial, this is the even polynomial. And another very popular kernel basis function called RBF. It's actually this. The RBF is really, I'm going to explain it. So each RBF kernel is a bell shape. And here I just show you with different center, and so that's why you got multiple. And there's another third popular basis called sigmoid. So sigmoid, it's very easy to remember. Sigmoid function has S shape. Just remember that, you're always going to know what the shape looks like. Sigmoid is S shape. And this is just different kind of S shape by varying that center and varying, this actually varies the center. No, I think vary the S. Yeah. So, sigmoid, we're going to talk about it later in the neural nets, and RBF, it's used very popularly in a lot of kernel-based regression models or a lot of cases. So that's why I will cover a bit about RBF basis and polynomial basis. So let's now see the real basis function, RBF basis. So the RBF basis again follows our y phi transpose theta representation. Each phi j is, we normally, when we see this is a RBF kernels, we write it as a k with parameter lambda j and parameter rj. And the concrete equation is exponential x minus mu j over to lambda j quadratic. So it looks like so complicated, right? But actually it's very, very simple if you say it verily. And for example, I'm just assuming I have, in this case, 4 different bases, 4 different RBF bases that really needs me to know where is the first RBF center and lambda, what's the second center and lambda, what's the third center and lambda, what's the last center and lambda. This is all predefined. Keep that in mind. Predefined. You need to define it in this cases, in this type of predefined basis regression. All right. So yeah. So I think I try to write again the theta. So because there are 1, 2, 3, 4 bases plus the pseudo, so you have to have a theta with theta 0, theta 1 until theta 4, totally 5 size vector theta to derive from data. Then the solution is the same, and then what is RBF basis? So this is a Gaussian RBF basis in the one-dimensional case, so which there's only one x. What you have is just this bell shape, and the R represents the center, the lambda represents the wideness. In the two-dimensional case, what you have is more like a hat, and it's centered at the parameter R. The wideness is controlled by the lambda. But it's still pretty abstract, right? Let's look at very concrete numbers. Okay, so think about there's a bell shape on top of me. There's a bell shape on top of me. I'm sitting at the center R. So the position I stand is the R. Right? If you just think about if I'm standing at R, right? R, let's just call that gamma. R or gamma, the radial basis, that R minus R equal to 0. What it gives me? 1, right? So that's my current R give me number 1. If I'm going left, a lambda, that's R minus lambda, or I'm going right, lambda, that's R plus lambda. This gives me what? 0.6. I'm going one more, 2 lambda. I think 0.1 something, yes? And then I'm going 3 lambda, to give me 0. Okay, so I hope this gives you a concrete feeling. What is this? The more you close to the center, the higher the values. If you are far away out the 3 lambda, you got almost 0 from this function, right? This function is bounded from 0 to 1, all in the center give you the largest values. And this is it. I mean, really, just if you're close to the center, it's high value. If you're 3 lambda left or 3 lambda right, 0. The contribution of this basis is 0. Okay, keep that in mind. Question about this? It's actually very important to remember. It's almost 0 from this function if you are far away in the left and right 3 lambda, more than 3 lambda. Okay. Yeah, so now you try to fit the data, and assuming this is you predefined RBF kernels, they're nicely distributed, and their center is C1. So in this case, it's like C1, C2, C3, and then they almost share the same lambda, assuming that's the lambda. Yeah, so this is the representation of your model. Your model really is this. There should be a beta 0 here. Yeah. So even though I talk so complicated, but the true full model is actually this, right? Now I've changed to beta, but it's the same thing, theta. Yeah, I should change it to theta. So yeah, so my fx is, so don't worry about this, I'm going to remove this. So yeah, we should just keep theta. Theta 0 plus theta 1, k lambda 1 x r1 plus onto theta 3 k lambda 3 x r3 in this case. Okay, so this is my representation. So now I'm going to feed some kind of data, assuming I just give you this data. So this is the y, this xy pair from my training data. And you draw a scatter plot, right? That's the easiest, it's the homework, right? Foresee it. So assuming my data look like this. So I'm trying to fit my data using the previous three bell, the three bell shape. What would you expect? I learned in theta 0, theta 1, onto theta 3. Yeah. Just make a guess. So in the end, I'm trying to fit this three bell by do a linear combination to fit my training data plotted like this, right? So it's highly likely, we're just speculating roughly. Theta 1 will be minus, right? So assuming like it's really centered at that position, and theta 1 will be minus, some kind of minus number. Some kind of maybe minus 0.5, because it also matters what's the largest number here, right? Assuming this is minus 0.5, and this is 5, and this number is maybe 2. It's not very proportional, but yeah, you get the idea. So it's highly likely what I'm going to learn is a combination like this. Y equals, yeah, that's defeated. It's like 0.5 k lambda 1 x fx. Better to write as fx r1 plus 5 times k lambda 2 x r2 plus maybe 2. It's a little bit tricky actually at this point. Yeah, I think this should work. K lambda 3 x r3, and it's highly likely the theta 0 is 0 because we're this crossing point, it's 0. So you can do a careful calculation because there's a homework similar to this. So in the end, this is just trying to fit the data. So in this case, I could have a positive, so that's why I got a positive 5 plus the second, and then the last one is minus. That's the other case with the data. So what's the problem of this type of fitting? Just try to think, speculate.
How do we get to R1 octants?
Great question. You actually do not know where to put R1 and also the wideness of the lambda, right? In this one, I just use my eyes to eyeball, right? Okay, so it's also not just this RBF kernel kind of basis function. You can have even a triangle type of basis function. There's a lot of flexibilities here, but you always need to design it. You need to know where's the center, what's the shape. There's a lot of design you have to put in there. And this page trying to show you a two-dimensional like I said, the two-dimensional RBF is more like a hat, right? So having the hat. And so this is a good design, and this is a bad design. So who can tell me, because bad designs are very easily to figure it out. And I already read the answer there. So this curve, this circle shows you the 3 lambda circle, 3 lambda contour. You can think about this, the 3 lambda contour curve. If your design of the basis spreading over the two-dimensional space like this, this is my x1, x2. Yeah, I can't, so this is actually a contour map. Again, now shift from surface map to contour map. Because it's very hard for me to visualize the surface map in the 2D case when there's so many bases. Because there's all those hops, right? So this is the contour map view. Just to clarify. This is the contour view. And the previous, they are all the surface map view because there's only one x here. This is the surface map view. So this is the contour map view, right? So it's very clear. If there are samples here, if there's a question mark like sample here, there's no way I represent it at all. Because all the contour of my basis will assign 0, almost 0 here. And then we're doing a weighted linear summation. Weighted linear summation of zeros, there's no way to have dramatic or reasonable numbers, right? That's why this is a bad design. Yeah, so I hope they'll get that. Okay, so now we covered basis function-based linear regression. Everything is the same. The only difference is you change the x into phi x. But there are a lot of design choices you have to make in designing the phi. Now, what's our issue here? The issue more general is actually called model selection. What I meant model selection, what we learned so far, so we haven't learned a lot of things yet, right? We only learned linear regression, polynomial regression, and RBF regression. But even we only learned so little, we already had so many choices to make. So what polynomial degree should I define as like upper bound to use to fit my line? Do I stop at 7? Do I stop at 5? This is actually one of the questions in homework 2. How to pick the right D. In the radial basis case, where do you put the center? What do you pick as the wideness? So if you look at this figure, I'm trying to just use all this RBF bases have the same wideness. That's already reduced 1 degree of freedom, right? But I still have choices about where to put them, the centers to make. And of course, you can also make them different size. I mean, different wideness, different lambda. And maybe one is really, really wide, the other is really, really narrow. That's also possible choices. And then on top, and should I use linear regression or should I use polynomial regression? Should I use like RBF regression? So let's come to this case. Yeah. For example, this case. Which one should I pick? I mean, I can fit a line there, right? I might also fit some kind of quadratic here. I can also fit like RBF, like 2 RBF kernel. I can even put a quadratic basis here, or a polynomial. One is 2, and the other is this shape, more like a 3. Which one do I pick? So this is exactly the task, or the very important step called model selection. And you're going to, as you learn more and more algorithm and more different type of models, and this gets more and more difficult. There's so many choices, right, to pick. So what's this principle or procedure you use to pick out the model? There's something called, there's a lot of variations, but in general, you want to pick a model to avoid underfitting and also to avoid overfitting. And this is just the problem in two extremes. What I meant underfitting is this. And this seems to be good, and this is overfitting. Overfitting is I fit so perfectly on my training data, but I don't think this is a good model for the future data. So this is the underfitting side, and this is, that's overfitting side, and this is the underfitting side. I don't even fit to the training data very nicely. So let's go on, like just put them together. Underfit seems to be good, overfit. And in the end, we emphasize many times is our generalization goal is to how well are you going to predict the future data draw from the same distribution. So I personally don't even see the same, talk about the same distribution. But the machine learning basic setting actually assumes training and testing comes from the same distribution. And our generalization is in the sense of future data from the same distribution. So the approach is to use for model selection to avoid underfitting and overfitting. Is in general the easiest is the k-fold cross-validation, and also a very easier case is the train test solution, which we're going to explain. So this is about what model type to pick, right? Linear, quadratic, or piecewise linear. And even inside a model, same model type, you still also need to select models, which I meant is, so this is a polynomial regression, right? But you have to select what D do you stop. Do I do 5 polynomial or 3 polynomial or 2 polynomial or 7 polynomial? So even you already pick the model type, but you still have to perform model selection for the inside the same model type. Again, still the same purpose, you want to generalize better. So this looks like the quadratic seems to be better, and the polynomial case 5 fit perfectly on the data, and this seems to overfit your data. What do you mean overfits, right? In the end, here and here, what I all meant can be reflected in the generalization performance. And how do you measure the generalization performance? Because this doesn't generalize well. This also doesn't generalize well. This generalizes well. And concretely, actually this means this has high cross-validation error, this has high cross-validation error, this has low cross-validation error. So let's first cover train test strategy, which we already covered from the first class. Sometimes people also call this leave M out or leave P out. So you just randomly select maybe 30% off from your training data. And in our setting, we already have the training matrices and test matrices N and M. Yeah. So then you just leave random pick 3 out. In here, they're just a circle, the hollow circle, the empty circle, and you train the linear model, and then you measure the error you make on those leave 3 out samples. So, but what error? So we already said, right? So here you use mean squared test error. And so this actually gives you, I'm not totally sure you can read the green color, so this just kind of speculated give you the train test error. The test error here is 2.4. Then you just use the same strategy on the training data. So by removing 3 points, you feed a quadratic line. And then you apply that quadratic model on that left out M data, and then you calculate test mean square error, and this time it gives you 0.9. And then you do one more model, which is kind of piecewise, fully connected model, And this actually clearly can't predict future better because it just fits too well on the training on that leave 3 out training data, and this gives you 2.2. So compare, this is 2.2 test error, this is 0.9, and this is like 2.4. So we pick this. This is using the train test strategy to pick the right model. It's a very, very easy setting, but there's issues. So this is extremely easy to implement. You just subsampling, like get that test data, you train the data, train the model on the training data, you apply this model on the test data, and you see which model win out among all the models. However, this, because you can't, if your data is small, reference data is small, you have 30% of data actually not used in the training. So your current evaluation is not ideal. Maybe that 30% added in the training can make your model better. So that's just one setting. It's kind of wasting 30% of data. And the other is maybe you just got an unlucky subsample. That subsample operation has so much noise and randomness related. So this time you sample this subset, that next time you sample another subset, the behavior may be completely not coherent. And this is what we meant, and in the future it means train test strategy has really high variance because the randomness of that subsample you get out to leave out as the test sample, especially in the smaller trained reference data cases. Great. So that's why people just actually use k-fold cross-validation a lot more, because this strategy can help you to use every sample both as training and also as testing, evaluation for the generalization era. So there are many variations, like 5, 10, and leave 1 out, and then we're going to explain what is it. So this is like 10-fold cross-validation. You divide your label data into 10 sub-folds. You just loop over each fold by using one fold as test, all the rest as training, and you train on the train part and then test on that current test fold. You loop over 10 times, and you report the average test error as the cross-validation error. So by this looping over, so the first 9 as train, the last as test, first 8 plus last as train, and then the 9th as test. So you use every sample there's a chance to be used as training and also to be as testing. And each one of this give you a model. Each fold case give you a model, and also give you a test MSE in our case, and you report the mean. So this is almost like, so actually, in a lot of settings, people call this validation error, but because what we cover so far, we call that testing error. So we're going to clarify that in the future slides. But for now, they are the same term. Just treat them as the same. So this is on that validation or test fold, epsilon 1, 2, 3, and then you just do a sum over and then over k. This is your k fold. This is the one you report. Cross-validation error. And there's an extreme case is called leave 1 out. Leave 1 out means every data sample is a fold. In total, you have n folds. So essentially, this is an n-fold cross-validation, but people normally call this leave 1 out cross-validation. You just loop over all the training samples by remove it, by use all the rest to retrain the model, and then use the second sample as test until you use the last sample as test. And this is an extremely expensive operation because you have to do n times of training, right? All right, so let's just use leave 1 out cross-validation on our smaller data. We remove this, and then we train a linear model. and then we remove that's the model we train, and then we evaluate the test area on that just trained model, and then we remove another, and then you just cover every samples because there's actually 9 samples in this case. You got 9 different fit, and you also got each sample's test area, and you just take a mean. What you get is 2.12. This is exactly how you're going to finish do that sample example in the homework 1. Leave 1 out by doing manually. And in our case, there's only 3 samples. Super easy. Yeah. And this has 9 samples. And also eyeball, don't use linear normal equation to do the calculation because it's not necessary, right? The reason why it's not necessary is when you have 3 points in total, by leave 1 out, what's the size of your training data? 2. How many points decides a line? 2. There's really no flexibility at all. That's the reason why I picked 3 samples, because there's no calculation necessary. You just eyeball. Okay? Yeah. So if you do quadratic line, same procedure, but just fit quadratic line. And this gives you hopefully lower MSE, cross-validation MSE, 0.9. And then you do the same thing on this kind of piecewise linear model, which is much more complicated. And the error, the 1 out cross-validation error will be much higher. And then again, because this gives you the smallest cross-validation error, you're going to pick this. So the whole thing is cross-validation error, and we use it, we think it's a good approximation of generalization performance. It can help you pinpoint when we're underfitting and overfitting. Questions? Sure.
What's the model?
What's the model?
So you have 9 models, you train 9 models. What's the
Good question. Yes. You already have 9 models here, right? What do you use in the end? That's something I could later. But just to tell you, normally after cross-validation, you use the best hyperparameter, the best model you picked, retrain a model on the full data by not leaving out anything. And that model is your final model. All right. So, so again, leave 1 out. When you have n samples, you have to train n models. This is fine for smaller cases, but when you have millions of samples, no way, right? Even thousands of samples, no way. So people just, train test strategy and then leave 1 out strategy. One is super cheap, the other is super expensive, but this doesn't waste data. This wastes data. So then people normally prefer something in the middle ground. It's normally like 3-fold or 10-fold. It depends on the data size, which one do you pick. It's a very tricky number actually to pick. And that's part of the homework too. So in this case, we just do 3-folds. We just do blue, and green, and purple. And you just remove the purple ones, then train the model, remove the green one, train the model, remove the what's the red? The green one, and then you train the model, and then you calculate those test error, then you report the mean. So hopefully in this case give you 2.0 for the linear regression, quadratic give you 1.1. This is all speculated just to let you know, but yeah. So actually you can do the full calculation. It's the trend is correct. And then you can also train this really complicated piecewise linear model to give you higher 3-fold cross-validation error. So that's why you pick quadratic. So let's just compare. This train test strategy is very noisy. The randomness of what you picked maybe ruin your selection because you might just pick a very unlucky, bad subset. It's highly likely because it's a random subset, right? And the one out covers all the samples, but it's super expensive. The operation is O(n), right? The O(n). When something is O(n), you really want to avoid it if each constant cost is high. So in our case, its training cost is super high, so you don't want it. So, but in the smaller cases, you can actually do this because the O(n) is very small, right? And, yeah. The n size is not very small, so you do 10 folds and then 3 folds, and n folds is identical to the one out. So do you pick 10 folds or do you pick 3 folds? So if your data is super large, normally you don't need to do 10 folds. But if your data are relatively small, but not too small. If it's too small, there's also issues with the 10 folds cross-validation. So there's a discussion we're going to make actually in the homework really about this, the influence on the model selection. So in the end, so there's a summary, I think actually go beyond this class. Cross-validation is a great protocol, a great procedure to do model selection. But cross-validation is not a very good choice to evaluate generalization error. And this may be a little bit beyond what we covered, but if you're interested, keep that in mind. It's a very good procedure to do model selection. So you did all this, you tried all the different models, you have the test cross-validation error, you just use the mean. Whoever give you the smallest, that's the model you pick. And this is cross-validation based model selection. Question here. All right, so so this is what we're going to cover in the full regression. Every content is involved in this. In the list, we already covered everything about optimization we want to cover. We covered the linear regression, covered the linear regression with nonlinear basis function. I'm not going to cover local weighted linear regression. I let you to read it because it's very related to k-nearest neighbor, which I'm going to cover later in the classification setting. Next class, we're going to cover linear regression with regularization, which is a very fun topic. So mostly here, this is about representation. The last linear regression with regularization is about the revision of the scoring function. So we covered representation today, we covered optimization on the previous class, then we're going to cover that module of variation of scoring function. It's really the regularized scoring function. And I think that's it.